Swayam Prabha. Digital India. Educated India.
So let's move into describing the data using the data types that we have. Till now, all we looked at was take a single variable and understand that variable. So for a single variable, what is the measure of location? Is it mean, median, which is the most appropriate given the data type or given the distribution, which is the most appropriate value. We looked at standard deviation, range, interquartile range to understand dispersion. We also plotted it in a histogram or a PP plot to understand whether it follows a normal distribution or what kind of distribution it follows, and therefore the shape of data. But in real life, majority of times we are not just interested in a single variable, we are interested in whether variable X, does it influence variable Y. So we are normally interested in at least at two variable level to see whether there is any association. Is a change in one variable, does it make a change in the other variable? Yeah. In a multivariate case, we are interested in if you have 10 variables and one of them is, we think, is kind of dependent on the remaining 9, how are changes simultaneously in the remaining 9 make a difference to the 10th variable? So let's start with the simple case of two variables. So if you have two variables and want to understand is there an association between the two variables, here are some measures statistics provides and we can use to get a better understanding of that. The example that we are going to use here is really we have 5 students and we have got height and weight. Conventional wisdom tells us that there is likely to be a relationship between the two variables height and weight. Weight is probably influenced by height in many cases. It is also important to note two different things here. One is, while weight is influenced by height, now height need not be the only influencer of weight. We know that the kind of let's say exercise habits a person has, the kind of dietary habits a person has, the inherent gene characteristics in terms of DNA and the propensity to put on weight and things like that, the kind of food a person eats, a lot of these things can influence weight. So we need to clearly understand, yes, we are trying to understand the relationship between height and weight, but height is not the sole influencer of weight. We also need to understand that there are some of these other characteristics that we talked about, like let's say the gene characteristics in terms of DNA, will have an influence on both height and weight. So that could be the causing factor that influences both height and weight. So one of the fundamental rules in understanding association is that yes, statistical tools tells you that there is a relationship between the two variables, but it does not confirm that there is a cause and effect. So the cause and effect is something which is much beyond these measures. It requires certain domain knowledge, it requires different kind of experimentation before we can come to the conclusion that there is a cause and effect between these two. Yeah. With that caution in mind, let's look at the two measures that commonly gets used to measure association between two variables. So if you want to know whether height influences weight in some fashion, one commonly used measure is what is called the covariance. The formula for covariance runs like this. So let's say height is variable x. So when the height of an individual, when it varies from the mean value of all the heights that we have, how much does the weight of that same individual vary from the average weight of all the data that we have? So essentially it tries to understand, as the height of an individual moves away from the mean value, how does the weight of the individual move away from its own mean values? So it's a kind of understanding the movement of two different variables away from the mean values, and how does that happen, and a quantification of that divided by n minus 1 to get an average value. Yeah. It's a good thing to remember, if we use the formula for variance as nothing but xi minus x bar whole square. That is how each value varies away from its own value. So supposing we go back to the original equation and substitute yi is equal to xi, we will get the same equation. So the variance is a very special case of covariance. So the variance is how much does a variable vary with itself. That's what it conceptually is. So let's look at if we use this computation and get a covariance value between height and weight, we will get a value of 81.56. Now again, we have some similar difficulties that we had with let's say in computing variance. Over there we had a large number, but we are getting a number like 81.56 and we have no clue about how to interpret this number. This gets further complicated when you have a different variable, when you add a third variable. So we looked at 81.56 is the kind of covariance that was between height and weight, and we had difficulty in interpreting this number. Supposing somebody has said, okay, now I have additional piece of data, which is I know how much each student burns in terms of kilocalories through exercises, and we have a set of data available for each student. And if the question that is asked is between height and calories burnt, which is associated more with weight. So we can also compute a covariance between weight and kilocalories burnt, and which is exercise, and we get a number of minus 0.224. Again, we have the same difficulty as we have with 81.56 in terms of understanding and interpreting this number. It's wrong to just compare the two numbers and say this one influences more than this. We will look at it as to why in a short while. But before that, let's look at the directions. So you have a plus 0.81, 81.56, which indicates that as the height increases, the weight also increases. So the direction, whether it's a positive or negative, tells you the direction of movement of the two variables. So a positive indicates that they move in the same direction, and negative indicates that they move in different direction. Interpretation: as the number of kilocalories burnt increases, the weight decreases, which makes sense. Now, why is it wrong to compare the two numbers? So supposing we had taken the calorie burnt through exercises not as kilocalories but as calories. So it's the same data, but the unit of measurement is changed from kilocalories to calories. And if we compute the covariance between weight and calories burnt, that's minus 224. So the first thing that we notice is that the covariance, the unit of covariance is nothing but the unit of the two variables that are used in measuring the covariance. So it is centimeter kilograms for between height and weight, and it is centimeter calories. It's kilogram calories for the covariance between weight and calories burnt. So first lesson is we have the covariance is dependent on the units of measurement. So you change the units of measurement, and if you compare magnitudes, you can come to wrong conclusions. Direction still remains interpretable. The direction, the sign of positive and negative, that remains the same. So direction of movement is something which you can interpret irrespective of what the units of measurement are, but the quantum is something which is not interpretable. So the second issue with covariance is really it's unbounded. You can actually get any value between minus infinity to plus infinity on the covariance value. So you can have very large covariance value and you will have the same difficulty in measuring your variance. Interpretation becomes an issue, and the covariance, as we just now saw, also depends on the units of the data in which it's measured and it's used to compute the values. So the way to overcome the difficulties with the covariance is really correlation. So is some way of standardizing the data before you compute the covariance. So the formula for covariance is nothing but correlation is nothing but the covariance value between the two variables divided by the standard deviation of x and standard deviation of y. Now by doing this, you automatically notice that we are removing the effect of units from the entire computation. And the second thing is by the mathematical, the arithmetic property of this definition is that this gets bounded between -1 and +1. So you could have a value only between -1 and +1 for any correlation done. Now this is called the Pearson's correlation coefficient. If you look at literature on correlation, you will find that there are many correlations. The Pearson's correlation is most appropriate for continuous data. So there are Spearman's correlation, which is used for rank data. There's Kendall's tau, which is used for categorical data. So there are, as I said, there are many correlation methods that are available. So depending upon the data type, we need to choose the appropriate correlation methods. So continuing on the Pearson's correlation, so it's covariance divided by the standard deviation of the two variables. So going back to the same data and computing the correlation between height and weight, we get a value of 0.86, and the correlation value between calories burnt and weight is -0.94, and the interpretation is that the calories burnt has a larger influence on weight in reduction of weight. So the sign tells you the direction of movement, as I said, but in terms of the magnitude of effect, the calories burnt has a larger magnitude of effect on the weight as compared to height. The formula for there are many different formulas for computational ease. So this is one of the formula which gets used most often. This is nothing but we had the covariance just divided by the standard deviation that we have. Visually to understand, so one is you can when you have a set of data, you can get what is called a correlation matrix between the set of variables that you have. So you can get numerical value for the correlations, but scatter plot as a tool provides a very good hint to the possible correlation values between any two variables. So here are some examples. So if you have a set of x values plotted on the x-axis and the y values plotted on the y-axis here, and if your data lies like this, now what it suggests is that as x increases, your y also in general tend to increase. So it's not absolutely true for every single data point that you have, but as a general trend that you notice that as x increases, y also increases. So essentially you got a line which or a band which goes like this. Now that band describes the movement between x and y, and supposing that this is the average between the two values, so this is the x bar and this is the y bar, as you go below x bar, the y also goes below y bar, and as you go above x bar, the y also goes above y bar, which essentially indicates that it's a positive correlation. And the fact that they lie in a very small band across on kind of the 45-degree line indicates that it's got a very high value in terms of the correlation value. So it's a big positive correlation that you have. The example which is just the reverse of that, which is nothing but it's in a good band on the but the slope of the line is -1 rather than +1. So so the sign is determined by the fact that as x increases, y decreases, and that's why the negative sign. But the value is high because it's still within a very small band within which all the data lies. And this is a data set which has got no correlation, because I can't say the way as x increases. So when you move from x value, let's take this point, as you take a data point here and you take a data point here. So as x has increased, in a big way, but y is not increased at all. Yeah, but for the same point here, so you also have a point somewhere here. So this point suggests that as x increased, y also has increased. So there is no definitive relationship that you can come to between the x and y. So it's lying in a very random fashion on the entire x and y spectrum. Therefore, the correlation value is very, very low. But I think if you are forced to fit a kind of a band within this entire thing, the band will look something like this, which has got a very, very slight positive slope, and that's why you still have the sign turns out to be a slightly positive. So it is a very small positive, but the strength of relationship is something which is absolutely low. So as I said, one of the good idea before you embark on any of the data science or understanding of data is to understand the relationship between the output value and the input values, various input values, get them as scatter plot to understand whether there is some kind of a relationship that exists. Let's explore correlations a little more through some small data experiments. So I had taken data of x as values of 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I constructed y as a perfect linear relationship of y is equal to 2x. So 2, 4, 6, 8, 10, etc. the value for y. That's scenario 1. In scenario 2, I constructed it as y is equal to 2x plus 4. So this is 1 into 2 plus 4, that's 6. So this is 6 into 2, 12 plus 4, 16, etc. And in third scenario, I took it as y and x cube, y is equal to x cube. So it's 1 cube, it's 5 cube here, etc. Can you make a guess about what kind of correlations that's likely to exist between x and y when y is equal to 2x and when y is equal to 2x plus 4 and when y is equal to x cube? The number suggests that there is a perfect correlation here, there is a perfect correlation here, and there is a very high correlation, but it is not 1. It's not perfect. Yeah. A further experimentation is what happens if I take this y is equal to x cube and not get the relationship between y and x cube, but take the logarithm on both sides and plot that. So I got ln x and then ln of y, which is ln x, which is nothing but 3 times ln x. Now if you notice that this looks very similar to y is equal to 2x, instead of y is equal to 2x, it's y is equal to 3x. So obviously the correlation turns out to be 1 in this case. So the idea from this is that the Pearson's correlation, because in this case the line is exactly passing through the origin, goes like this. This case is nothing but the line is a perfect correlation, but that does not pass through the origin, it's got an intercept of 4. And the third case here has got a graph like this. Yeah. So the Pearson's correlation provides a direction and strength of linear relationship. So the idea is, if it is a linear relationship that exists between the two variables, Pearson's correlations returns a very, very high value. But if it's a non-linear relationship, it may return a high value, but it is not necessary. So let's explore the y is equal to x cube further to understand what we can do with it. Supposing we had converted the data into ranks. So again I have the same, the x value is 1 to 9 and the y is x cube, which is 1 to 729. So when you convert this into ranks, it again converts it into ranks 1 to 9, and when this is converted into rank, this is converted into 1 to 9. Now you notice that there is a kind of a perfect sync, a linear sync between x and y is equal to x cube. But what you have done by converting the data into ranks is that you lost certain properties of the data. So I can't do any divisions any further. So I can't, you notice that it's a ratio data which is now converted into a ordinal data. So we know that the ordinal data we can use a median, but we cannot use a mean, for example. Yeah. So we are losing some ability to manipulate the data when we convert the data into ranks. But to understand relationship between two variables, if you use the Spearman's correlation, which is defined as rho 1 minus 6 sigma d square, and d is defined as the difference in rank between the x and y value. So it's the difference in rank between these two, and that's the d that we have. Summate it, use this formula, you actually get a value of 1. So when your data does not satisfy a linear relationship, and when the data is not metric, a Spearman's correlation is a far better indicator of an association between two data points as opposed to the Pearson's relationship. So let's get this. So if there is a linear relationship, Pearson's correlation will return a very high value. But if the Pearson's returns a very high value, it does not necessarily mean that there is a linear relationship. So you need to use the scatter plot and the data value in conjunction together to come to a conclusion as to whether there is a linear relationship, linear association. If the Pearson's correlation returns a lower value, it's possibly worthwhile to do let's say a Spearman's correlation to see whether and if that returns a very high value, it indicates that there is a correlation, but the relationship is non-linear. As I said, there are certain data types like nominal data are not, where you cannot use either Pearson's nor Spearman's. You might have to use other association measures like Kendall's tau or chi-square. So those are measures of relationship or association between variables. We will look at them at a later date. So coming back to where we started, so what we have looked at till now is when you have data of this nature, we can take a single variable, understand its mean, median, mode, to know what's the kind of a single value that defines the data the best. We can also look at standard deviation, range and interquartile range to understand the dispersion of the data. We can also do a histogram or a PP or a QQ plot to understand the distribution or the shape of the data. Yeah. So that's for every single variable that we have. Then when you want to look at two variables together, we can use a Pearson's correlation to understand whether there is an association between two different variables. What we are now going to do is really to take this is a sample of a data, so I am going to use a larger data set to arrive at some standard outputs that you can use to use descriptive statistics to understand your data better. So that's what we are going to do now. We have a total of 43,155 records. The minimum value that we encounter is 100, the maximum we encounter is 149,000. So the range which is max minus min is practically 149,000. So that's the range in which the data values lie. You look at the mean here, the mean value is 6140.35 and the median is 3499. So whenever you encounter large differences between mean and median, it clearly indicates to you that there is a kind of a skewed distribution. So what it means is that, so you have 50% of the data that's lying here, that's where your median is getting defined, but your balance 50% does not lie in the same range here, that lies in a very large range. So all these extreme values are, which may be correct, are pushing the mean towards this direction. So you are it's very likely that when there is a big difference between mean and median, that there is a very skewed distribution is what is making this happen. The other thing that you can look at is the standard deviation is 7,900. So the range was is close to 149,000, and standard deviation at 7,900 indicates that the total data spread is something equivalent to 18 to 19 standard deviation. So your total data spread that you have because of this long tail is kind of 19 sigma. Yeah, again indicative of a very skewed distribution you have, because a perfect normal distribution is likely to have within a very small tolerance limit plus or minus 6 sigma. The minute you go into these kind of levels, it's clearly indicative of a skewed distribution. You can also look at this as a histogram. So this part of the histogram is when the data was plotted as it is. So you have the price on your x-axis and the number of instances in which the data is appearing. So you notice that close to 36,000 actually lies in the range of 0 to 25,000. So that's the range in which it is lying in. And then there is a kind of about 3,000 to 4,000 cars in the 25,000 to 50,000 range, and it goes on, and then it peters down into very small numbers. There are cars, we know that up to 150,000 there are cars that are available. They don't show up here because they're so thin. So if you looked at this distribution is really, it's actually a distribution like this. That's the distribution that you have. So it's not even a normal distribution that we have. Yeah, it's a kind of an exponential distribution that we have in this. As I said, a lot of data science models are particularly interested in knowing whether your data is normally distributed. Now, when we had our y is equal to x cube, when we were looking at correlations, you remember that we converted both sides by taking a log transformation. So one of the way to convert a non-normal distribution into a normal distribution is also to use transformations. So just an example here to use what happens if you convert the price data into log price. So what is plotted on the x-axis here is not price but logarithm of price, and the number of instances are plotted in the y-axis. You see that now this looks a lot more closer. So when I want to take this entire data into a kind of a statistical model at a later date, I must keep in mind that transforming the price into a log price satisfies at least the distributional conditions that some of the statistical models will be looking at. Therefore, this is one of the options that I have when I want to move into a statistical model at a later date. Let's look at another continuous data, which is we've used age. So the age is computed. So the original data, if you remember, had a year of registration. So by using a referral year 2018, I think, each of this data is converted into age. So we know that something which is registered in 2012 has got a year of 6. That's a age. Something which is bought in 2010 and registered in 2010 has got an age of 8, etc. So the age is a continuous variable. It can take discrete values. It does not, the way we have computed it, it cannot take a fraction, but it can take a discrete value. And again, we have 43,000 records. Here we have, the first thing that we notice is that the minimum is 0, maximum is 76. So, and the standard deviation is 7.86. So the data is spread over kind of 10 sigma. So it does not confine to a 6 sigma, it goes up to 10 sigma. But if you look at the mean and the median, they are very close to each other. So we are not sure whether there is a skew, or if there is a skew, that skew is equally distributed on either side. So you have some cars which are offered at which are very low in age, and there are some which are very high in age, and the majority of them are lying in the middle. So when in the previous case, when we had a mean much higher than the median, we clearly knew that, listen, there are some very extreme values on one direction that probably made that mean being much higher than the median. Here we are not sure whether that's the case, or whether it's some kind of a distribution, other kind of a distributional issue. So to understand that, if you plot the box plot, now the box plot tells you that the middle 50% of the data lies somewhere here, and then the whiskers are drawn at 1.5 times. So this is the IQR, and this is the IQR on either side. Okay, and you find that on the upper direction there are lot of numbers that are lying on the other direction. So essentially that's a much longer thinning that is happening on the larger age side. So you have, I think when you get numbers like 76, it's really indicative that there are a whole series of probably vintage cars that are being put into the thing, and that's what's making the spread of the data much higher than what it is. Now on this issue of 1.5 here, this is a kind of a standard output that you will get in most of the programs, but depending upon your domain knowledge, you might say, listen, I don't want to look at it as a 1.5, but I want to look at it as a 3.0. That's your option. So you can choose when you actually create these, and so you will learn more about this when you learn how to create these graphs. When we do not have a continuous variable, in our data we had lots of categorical variables, and the best method is to understand the frequencies and mode. So we had a vehicle type, so 1, 2, 3, 4, 5, 6, 7, 8. So there were 8 different vehicle types that we had. You had the limousines, small cars, the buses, cabrios, coupe, etc. So the total data is plotted back into the counts. So all of this would add up to our 43,000 plus, and then the percentage is plotted. So it tells you what is the dominant. So this is your modal value, mode 1, this is your mode 2. So this is the second largest item that's there. So if you are looking for sparsity, so to say that, listen, can I reduce, can I club this data, I'm really not interested in some of these things which have got a very low value. So you might say, listen, I might want to keep this as a separate category, this is a separate category, this is a separate category, but can I club these 2 or can I club these 3? Because I'm looking at chunks of data which is at least 10% of the total data. So if you take a decision of that nature, which you may to reduce the number of possible options that are there in the vehicle types, so this is a tool that enables you to do that. It also tells you that close to 60% of any vehicle that's coming into the used car market is either a limousine or a small car or a station wagon. Supposing you had also a manufacturing number which says that in the last 10 years the limousines plus small cars plus station wagon that was actually produced were only 40%. Now that's an indication which says that, listen, people, there are more the limousine, small cars and station wagon comes into the used market far more than the rest of the vehicles. So the rest of the vehicle types do not come into the used market as frequently as these 3 types are. So you can make a comparison between, let's say, what's produced and what's available in the used car market to see whether there is a consonance between the 2 numbers. So those are the kind of analysis that you can do, but at a simple level it tells you what are the dominant categories that are available within this. You can also look at this visually by looking at a bar plot. So you find that there are distances. The difference between the histogram and the bar plot is that you have these gaps that's there between the categories. So you know that these are distinctive categories. So at a snapshot you can see whether there's a difference in limousine and small cars. Let's, for argument's sake, that let's say that we also had, for example, the city in which these cars are being sold at, and let's say you had about the big towns and small towns. By taking a bar plot of this breakup for big town vis-a-vis the small town, we can actually compare and see, is the profile of cars that are coming into the big town and the small town, are they similar or are they different? Yeah. So you can do analysis of that nature to understand association between 2 different variables. Another example of categorical data, we had gearbox, which is either manual or automatic. We find that majority of the vehicles that came into the market were had manual gearbox, and very small number in automatic. When I say very small, relatively it's a percentage number. Again, a bar plot. So it's just an illustration of the same thing using another data piece. What's more interesting is when we start getting into understanding association between different data pieces. So you have two categorical data. So we looked at in the previous slides, we looked at the vehicle type, what kind of distribution the vehicle type has, and what kind of distribution the gearbox has. But is there a relationship between the vehicle type and the gearbox? So question could be, listen, I mean, what are these manual ones? Are they predominantly of a particular type of vehicle? If that is the kind of question that gets asked, so you can generate a table which talks about all the vehicle types on the rows, and whether it is automatic or manual. And what we have taken here is really the column percentage. So across the column, this will add up to 100%. So the interpretation here is amongst automatic cars that are being put into the market, 23.96% are station wagon and only 19.27% are manual. Now we can see at a later date using some more statistical tools as to whether this is a significant difference or whether it's not a significant difference. It's a little more stark when it comes to a small car. For example, out of all cars which are put into the market with automatic transmission, only 8% are small cars, whereas out of all cars which have got a manual transmission, 28% are small cars. It's likely that again we need to do a kind of a test to understand whether this is a significant difference, but intuitively it appears that this is a much larger difference that you can notice between these numbers, and therefore the manual has got a lot many more of small cars compared to the automatic transmission. So you can compare profiles of two different profiles, and we will use, when we do the significance testing, we will do something called a chi-square test to understand is there an association between the vehicle type and the gearbox type. So it's to understand associations between two categorical variables. Yeah. Visually, you can also plot this as so the same percentages are plotted. So the vehicle types are on the x-axis and the percentage which is proportion is on the y-axis. So clearly by straight away looking at it, we see the fourth item has got a much longer bar here, and the seventh item has got this value, whereas the seventh and sixth are fairly, the distance between them are much lower here. So you know that visually that there is a difference in the profile of the type of car if what is given is a gearbox type. Yeah, so this is for automatic gearbox, this is for the manual gearbox. What if you want to understand kind of relationship or association between a continuous variable and a categorical variable? So again, when you are looking at it through numeric measures, what is plotted over here is all the measures that we have. So the price is what we want to understand, and how price varies across limousine, small car and station wagon. So we know that there are 8 different types of vehicle type, but for this illustration I have just chosen the 3 vehicle type, which is limousine, small car and station wagon. Some of the things that you can quickly notice are the mean values here. So the mean value of a limousine is much higher compared to a small car, but it is more or less similar to the station wagon. And the difference between the mean and the median, which is indicative of a kind of a skew in data shape, persists across all the 3 types. So it's not that the station wagon is a perfectly distributed in terms of shape, whereas limousine is skewed distribution. So the difference between the mean and median for the 2-3 different classes indicates to it that whatever skew that exists in the same direction exists for all the 3 vehicle type categories. So visually this is what you can do with that, and you can also look at a box plot to see. So the box plot plots this entire thing, which says that, so this the difference in mean value here clearly indicates that the mean value for the small car is much lower here, and all these data points which lie above this 1.5 times the IQR are considered as extreme values, and these are values here which is just about, seems to have some very large values of more than 80,000. So if you want to, you might take a decision and say, listen, I just want to remove these data points before I recompute my means. Now what difference would it make is something which you need to really check out and do it. So this is one way of understanding outliers that exist within your data. If you can also understand a relationship between a continuous and a categorical variable by what is called binning. Let me just go back to the previous slide to quickly tell you that, you know, this is the kind of mean values that we had, and the overall mean values is about 6140. So I had broken up the total data into two sets, those which are which had a mean value of which had a price value of greater than or equal to 6140.35, and those which had less than 6140.35. And within that we want to know what is the kind of gearbox that exists. So again, this adds up to 100% here. So essentially the interpretation here is, if the price of a car is less than 6140, 85% of them are likely to be manual transmission, whereas if the price of the car is greater than 6140, only 61% is less than are likely to be manual transmission. So there is a very clear difference, which essentially indicates as the price goes up, the kind of car that I am likely to be looking at is likely to have an automatic transmission. There is a higher probability of that having automatic transmission compared to a manual transmission. So that's a way you can interpret some of these data to understand the relationship. So as price increases, the more likely that it is an automatic transmission car. A more tougher way to look at some of these data is in graphical scatter plot format. But what is interesting here is we have three different variables that are clubbed. So there are two continuous variables and one categorical variable. So the x-axis is the age of the car in years, the y-axis is the price in dollars, and the dots here indicate all the yellow dots are automatic transmission and all the blue dots are the manual transmission. Yeah. Slightly difficult to make sense of what is the difference between the yellow dots and the white and the blue dots, because they seem to be kind of spread rather only in these areas where we see only concentrations of blue dots, not too much of kind of the yellow dots. But one thing that you can notice is clearly is when the age is less than 20 years, the kind of spread in price is much higher compared to when the age is greater than 20 years. So here again you clearly see that there is a relationship between age and price. It is as the age goes up, are we able to conclusively say the price goes up? No, we cannot. It can go up, it cannot go up, because you have, for example, very high value of prices, you have some data points here as well as you have some data points here. Okay, but what you know is the dispersion that lies within. So the shape of the data when the age of the car is less than 20 years is very different from the shape of the data that when the age of the car is greater than 30 years. Now supposing we had some very clear pockets of yellows. So no, that's not the way the data lies, but if you had a kind of a pocket here where you had only yellow dots and no blue dots or very few blue dots, then you can start making certain conclusions about how to split the data so that you can make better models. So you can make multiple models, and some of the decisions related to, do I build just one model or do I build multiple models and then put it together, are kind of taken by using these kind of plots. But as I said, most of your software offers even more options. They can you can start using shapes in addition to colors to add a fourth variable. But from a practical point of view, I find it very, very difficult to read. So with so many data points, it becomes kind of impossible to read beyond 3 variables. Even 3 variables, unless you are lucky and get certain very clear patterns, it's worthwhile exploring, because if you do get a clear pattern, that's what we are looking for in data and a lot of data science. So it's useful. Let's look at the other area where we started, when we looked at 2 variables, 2 continuous variables, you can look at the correlation matrix. So the correlation matrix here is really talking about, so these are the 4 continuous variables we had: price, power, PS, kilometers and age, and that's put down, and this entire diagonal is all 1 because that's correlation with itself. So the 0.57 is the correlation between price and power PS. Here again, whether a correlation value is good, bad or ugly is something which is very domain specific, is something that you look at as to what you, so normally in engineering domain, if you get, let's say, 0.8 plus is considered as a good correlation. In financial domain, 0.4 plus is considered as a reasonably good correlation. So the idea is, the larger the number, the greater the chance of a linear relationship that exists between the two sets of parameters. I would have been very, for example, the power PS and kilometer, I know that it's got a very, very low number, or even this power PS and age. So there is no definitive relationship that exists between age and power PS, kilometers and power PS, etc. But with price, power PS seems to have a reasonable correlation, not the best of it, kilometers and the age. Not conclusive, but you can, if I need to identify candidates which are likely to determine my price, I would think power PS and kilometers would do far more than age, which is a little bit of a surprise. Yeah. Let's look at the other area of usage. If you remember that when we talked about why we do descriptive analysis, one is to understand the data types and therefore what kind of models that we can use. The second area is really understanding data quality. These are not standard outputs, so these are something which you need to construct. You can choose, you can design your own construction. So I'm using this particular construction. So you can take a variable and get, so the first 2 are the counts of records. So if you notice the very first slide that we looked at the data, there were gaps that existed in the data. So please be aware that most of the data, when you get it in the raw format, is really dirty. So it's not clean. So it's inbuilt with mistakes. So there are mistakes related to range. So you will have a year which is, let's say, 1750, which really doesn't make sense. Or you can have a gap where there's no data available at all for a particular variable in a particular row. So it's a good idea to write a program right in the beginning which plows through the data and gives you these outputs. So for continuous variable, look at the frequency of the number of records which are missing, the percentage that is expressed as a percentage of the overall data pieces that you have. Cardinality is really the number of distinct values that are appearing. So what it essentially means, the 2393 means, though we have 43,000 odd data rows, there are only 2,393 distinctive values that exist within that. Yeah, so the maximum could have been 43,155. So each car would have been differently priced, and each car, no two cars had the same price, and in which case the cardinality would have been very high. Cardinality is useful in determining certain types of graphs, certain types of intervals that you want to get for your histograms, etc. Then you look at what's called the 5-point summary along with mean. So you have the minimum, the Q1, Q2, mean, Q3 and maximum. So the difference between the mean and the median straight away tells you skews. The max values compared to the mean value. So essentially the range, the understanding between range and standard deviation tells you the kind of spread, the kind of outliers that are likely to exist within the data. You should also, this is just a continuation, I didn't put it on the previous slide because I could concatenate it. These are something which is not going to appear automatically, these are something which you need to manually populate. So you take a variable and say, listen, what is the price? So obviously this cannot be a negative value, for example. So you can define certain conditionalities and then get data rows which do not conform to those conditionalities. So which essentially are certain decisions that you need to take to understand, so do I discard the row or do I do something else? So can I remove the value and take the average of the rest of the values and put it over there? So those are kind of decisions that you want to take. We knew that most of the cars manufactured were nothing had less than 10 HP. So if you had 10 HP as the power PS, so these are records that you want to do something with. The kilometer could have been 0, but the kilometer couldn't have been, let's say, 30 million. So it's impossible. This column is really related to understand whether there are logical linkages that you can understand between data. For example, if you looked at we had certain brands of data, cars, and there are certain types. So you have, let's say, a Volkswagen limousine, and then there's a particular subtype. From the manufacturer definition of that car, we know the kind of range within which the power PS will have to appear. Whether there are certain types of cars which can only have automatic gear, cannot have manual gear, etc. So this item is really to spell out the kind of logical linkages that each variable is likely to have with the other variables, and see whether you can use this sensibly in cleaning the data, in preparing the data for any further analysis. Again, when it comes to categorical variable, obviously the mean and the median, etc., doesn't make sense. So you really have, you have the vehicle type, where we had about 11%, 10.38% they were missing data. So you need to define a strategy and devise a method to see what do we want to do with it. So do you want to just remove this rows? With large amounts of data, you can say, listen, I will get rid of some of the rows. But supposing you found out that all this where there's a missing vehicle type, the value of the car is much more than $20,000, whereas our mean is only $6,000. What it essentially means is that by removing this, you are removing one specific pattern that exists within the data. So you may then decide, listen, I don't want to leave the data, I want to do something else with it. So which is certain imputation strategies that you will learn as we move along. Cardinality, so there are 8 vehicle types. So do I want to reduce it? So that's kind of decision that you want to take here. You get the first mode, you get the second mode, you can also have third mode. So if you find data sets where there are too many categories, so you want to get multiple modes. Again, look at limits, so values that it can take, values it cannot take, and logical linkages. Doing this as an initial output is a wonderful way to start your data quality mission, because like in all fields, the garbage in, garbage out works wonderfully well in this field. So if your data is not clean, so all these statistical measures and certain domain knowledge which comes in the terms of limits and logical linkages can help you at a quick snapshot understand the quality of your data and the kind of investment that is required to get the data to a shape which is statistically modelable. This is just further examples of fuel type categorical data. So more categorical data and the kind of linkages that one sees. That's it in this session. So we'll see you in the next.